4.12 Transient Analysis. So far we have considered the thermodynamic analysis of open systems in steady state. The steady state indicates there are no changes in thermodynamic properties with time. In the energy balance equations, the left-hand side term dE over dt equals 0 for steady state condition. Also, there is no change in the mass of the control volume with time. So dmCV, mass of the control volume over dt equals 0 under steady state condition. So this greatly simplifies the analysis of open systems. However, there are circumstances when the properties and state change with time. It is called transient process or unsteady process. So mass of the control volume may vary with time. So dm of the control volume over dt is not 0. So we integrate the mass balance equations over some period of time t. So time is 0 at the initial state, and the time is t at the final state. So mass of the control volume at t minus and mass of the control volume at time 0 equals mi is the amount of mass entering the control volume through inlet I during some period of time t. Summation is used for multiple inlets. Subtracted by me is the amount of mass leaving the control volume through exit E during the some period of time t. Also, summation was used for multiple outlets. We can also apply the energy balance relations for open system under transient process. So the general forms of energy balance equation is shown here, and dE over dt is not 0. So energy of the control volumes is du kinetic energy of the control volumes, potential energy of the control volume. So we neglect the kinetic and potential energy change in the control volumes as the system is stationary. We also neglect the kinetic and potential energy change of the flows that enter and leave the control volume, as the changes are assumed to be small. Kinetic energy, potential energy drop out. So we integrate the equation over some period of time t. Usually in transient analysis, we consider a uniform flow process to simplify the analysis. So the uniform flow process means that the properties of the fluid entering and leaving the systems are uniform and steady. So we can assume enthalpy at the inlet and outlet are constant with time. From these equations, we can take enthalpy out of the integrations since it's not a function of time. So we can take the integrations of the energy balance equations, and the energy balance becomes the typical examples of transient analysis include a charging an empty container with a fluid, or discharging of a fluid from a pressurized container. Let's first take a look at a rigid tank that is connected to a high pressure pipeline through a valve. So note that it has only one inlet and there are no other ports. So initially the tank is empty. And when the valve is open, the tank is supplied with a fluid from the pipe until the pressure equalizes. So the fluid is going into the control volume and the mass increases with time. And the pressure and temperature of the tank is continuously changing as the fluid is charging the tank. The pressure and temperature of the tank is continuously changing as the fluid is charging the tank. We neglect the kinetic and potential energy change in the control volume as the system is stationary. And the energy balance for charging a system with a single inlet is shown here. It can be further simplified if the tank is initially empty, then this term goes to 0. And if it's an adiabatic process, Q also drops out. So the internal energy of the tank at the final stage is equal to the enthalpy from the high pressure pipeline. When the tank is initially pressurized and the valve is open, and the tank will be discharged, flow is leaving the tank. So energy balance equation is shown here. So in this equation, we see enthalpy of the fluids that leave the system. Let's say an example. A tank having a volume of 0.85 meter cubed initially contains water as a two-phase liquid vapor mixture at 260 degrees Celsius and a quality of 0.7. So the temperature and the quality of the system are given, so we can fix the state. Saturated water vapor at 260 degrees Celsius is slowly withdrawn through a pressure regulating valve at the top of the tank as energy is transferred by heat. So there is a heat transfer across the system boundary and it maintains constant pressure in the tank. So the water vapor is leaving the systems, but since the heat is supplied to the systems, it can maintain a constant pressure. Determine the amount of heat transfer in kilojoule. Neglect all kinetic and potential energy effects. On a TV diagrams, the initial condition is inside the vapor dome since it's a mixture. And it undergoes a constant pressure process, so it moves horizontally. And the final state is saturated vapor, so state 2 is on the saturated vapor line. So the quality is 1 at the final state. So we can write the mass balance equations. So it has a single port and there is no mass going into the system, but mass is leaving the system. So this is the mass balance equations and energy balance equations. There's no shaft work in this system, so W drops out. And we neglect kinetic energy change and potential energy change. And there's no mass going into the system. So energy balance equations is simplified. And it can be written using the energy balance relations. And integrate this energy balance equations from 0 to T. And we solve it for Q dot. And we use subscript 2 denotes final state. Subscript 1 denotes the initial state. We can fix the states at the initial state and the final state. Let's determine the mass and the internal energy and enthalpy at the initial and the final states. So at state 1, temperature and qualities are given. So we use table A2 at 260 degrees Celsius. We are going to use saturated liquid, saturated vapor properties. The internal energy at state 1 can be calculated based on the quality at 260 degrees Celsius. And the specific volumes can be also calculated based on the quality. The specific volume is defined as the volumes over mass. So from these relations, we can determine the mass at the initial conditions. At state 2, we know temperature is still 260 degrees Celsius and quality is 1. The saturated vapor takes up the tank. So again, use table A2 to determine the specific volumes, internal energy. And the mass at the state 2 can be also determined based on the specific volume. Volume doesn't change, 0.85 meter cubed. So mass is known, internal energy is known, mass at the initial condition is known, internal energy is known, mass is known, mass is known. The only unknown is enthalpy leaving the tank. So what we are going to assume is the uniform flow process. So the properties of the fluid leaving the system is uniform and steady. So we are going to determine HE, so enthalpy of the fluid leaving the system. So in the problem statement, a saturated water vapor is withdrawn through a pressure regulating valves. So we note that a saturated vapor is leaving the system. So we can determine enthalpy of the vapor at 260 degrees Celsius. So enthalpy for the saturated vapor. This is HE. So Q dot, plug in the values. So we were able to determine the heat transfer rate to the system. So Q dot is positive, which means that heat is transferred to the system. Let's say another example. A rigid tank whose volume is 2 meter cubed. Rigid tank means the volume doesn't change. Initially containing air at 1 bar, 295 Kelvin, is connected via valve to a large vessel holding air at 6 bar and 295 Kelvin. The valve is opened only as long as required to fill the tank with air to a pressure of 6 bar and a temperature of 350 Kelvin. Assuming the ideal gas model for the air, determine the heat transfer between the tank contents and the surroundings in kilojoule. Let's draw a diagram first. So this is a system boundary and it's connected to a large tank by a valve. And the volume of the tank 2 meter cubed and initial temperature 295 Kelvin. Pressure 1 bar. And the final temperature 350 Kelvin. Pressure 6 bar. So the fluid is going in to the control volumes from a large tank. So large tank has a pressure 6 bar and temperature 295 Kelvin. We want to determine the heat transfer between the tank contents and the surroundings. Let's first apply the mass balance. This is transient heat transfer problems. dm over dt is m dot mi dot minus me dot. Fluid is going into the system, but there is no fluid going out of the systems, so me drops out. And apply the energy balance equations. There is no shaft work, W dot drops out. There is no mass leaving the systems. The simplified equations becomes, plug in the energy balance equations and integrate the equation from time 0 to t. Or we can write m2 u2. So we solve it for the heat transfer to the system. So air is considered as an ideal gas, and the internal energy and enthalpies are only function of temperature. So we can use thermodynamic tables to determine the internal energy and enthalpy of an air. And we're going to use the ideal gas law to determine the mass at the initial and the final state. So ideal gas law states pressure times volume equals mRT. So at state 1, M1 is P1V over RT1. So initially it was at 1 bar. Mass of the final state can be also calculated using the ideal gas law. So mass at the initial and the final states are calculated. Next, we are going to determine internal energy and enthalpy. So initially the temperature is 295 Kelvin. So use the table A22, ideal gas property of air, temperature 295 Kelvin. The internal energy at the initial condition is here, U1. And the internal energy at 350 Kelvin is shown here. And we also need to calculate HI. Again, we are going to assume the uniform flow process. HI is the enthalpy of the fluid going into the tank. So this is the enthalpy of the fluid from the large tank. The temperature is 295 Kelvin. So HI is here. So we plug in values. So the heat transfer to the system is negative 339.7 kilojoule. This means that heat is removed from the system.